Okay, so now let's talk about the preparation of alkynes real quick. So how do we make alkynes? Well, so first of all, let's just remind everybody, we know from back in chapter 7, actually, we were talking about elimination reactions, and that's how we can prepare alkenes. And that is if we take an alkyl halide in the presence of a strong base, we have this elimination reaction that produces an alkene. Good news is we have a very similar or analogous type of way of forming alkynes, and that is to start with an alkyl dihalide, right? So now I have 2 bromines or 2 halogens. If I treat this with a strong base, I can get an elimination 2 elimination reactions, and then I will produce an alkyne. Okay, so just like, very analogous, rather not just like, but analogous to what we had with the formation of alkenes through elimination reactions, we can form alkynes through elimination reactions as well. Again, we just need to have a dihalide. Okay, and so let's just see the mechanism here. In this case, we would have an E2 type elimination reaction. Our base is going to grab that hydrogen there at the same time that that hydrogen will form a new new carbon double bond and kick off that bromide leaving group. So then we have now an alkene, but we also have this halogen still remaining, right? Because it was a dihalide. And so we can just repeat the process again. Our strong base is again going to grab that hydrogen. It's going to come down and now form a new pi bond. This will be our triple bond at the same time that that bromide gets kicked off. Okay. This example is with it's called a geminal dihalide. This gem word right here means that the halogen is bound to the same carbon. Okay. We can also see, well, we would see the same thing with what's called a vicinal dihalide, and that is if our 2 halogens are adjacent to one another on carbon bonds. Both will produce, in the presence of strong base, an alkyne. Okay, so it doesn't matter if they're both bound to the same carbons or if they're bound to next door neighbor carbons, you will still get the formation of an alkyne in the presence of strong base. Okay, so let me just show you one kind of common base that's used. You're going to see this one a lot, and we'll see at the end, by the end of this chapter, why this one's so popular. If we use an excess, and notice that excess is sort of abbreviated with an X and an S, clever, of sodium amide. Amide, and again, this is going to be a very popular base. It's an incredibly strong base, very popular in this chapter. Amide is an amide ion, rather, is that ion right there. It's very annoying because when we were learning functional groups, this was also, I actually call these amides and the other one an amide. A lot of people call these amides as well. They have the exact same spelling. If you pronounce them the same, that's fine. Unfortunately, there's a difference between an amide or an amide functional group and an amide or an amide ion. I guess just to keep them straight in my mind, I call these amides and these amides. That's not necessarily right. That's just my weird way of doing things. Okay, but bottom line is when you see excess sodium amide, sodium amide or something like this, you are thinking we have a lot of very strong base. So in this case, I have, let me get rid of this. In this case, I again have one of those geminal dihalides. In the presence of strong base, I'll form an alkyne. Okay, so this is pretty cool because starting with, for example, an alkene, we know that we can react these with a halogen, so in this case, liquid bromine, in order to form that dihalide. So then we can turn around and treat this with our sodium amide or some strong base. It's important to follow this up with water especially the case of a terminal alkyne. We'll see why that is again towards the end, but just note, and we'll be able to form a triple bond. Okay, so it's actually a pretty powerful thing to be able to just treat these dihalides with strong base in order to get this new functional group.